Okay, welcome everyone for our webinar series on acoustic, thermal, and mechanical metamaterials. Today we have the great pleasure to welcome Dr. Zoïs Moitier from the Department of Mathematics at the Karlsruhe Institute of Technology in Germany. And Zoïs is going to talk on nonlinear Helmholtz equations with sign-changing diffusion coefficient. Zoïs, the floor is yours.
Thank you, and thank you for the organizer for the invitation. So yes, I will talk to you about nonlinear Helmholtz equation with sign-changing diffusion coefficient, and this is a joint work with Rainer Mandel and Barbara Werfel, also at KIT. I'm sorry, my webcam doesn't seem to work, so you will have just to listen to me. So the goal, so I will introduce my motivation model, and then we want to do some non-linear equation. We need to first talk a little bit about the linear part, and then we'll have two kinds of non-linear results, some bifurcation and variational results. So let's go into the motivation. So the motivation is to combine, to see what happened when you combined some nonlinear effect and metamaterials in let's say electromagnetic setting. And so, for example, if you take a Maxwell waveguide with the Maxwell equation, here we are, and E and D denote the electric field and / induction. H and B represent the magnetic field / induction. So from these two equations, we need to add material law. And for example, we can have Kerr nonlinearities. So that means that, for example, the field D will be equal to, so epsilon is the permittivity, plus the third order subsibility times a cubic term on E. And for B, we'll just take the permittivity times H. And this is for the nonlinear part. And we also want to introduce metamaterials. So for dielectric materials, we will have epsilon and mu are positive, but for example, for negative index metamaterials, epsilon or mu can be negative. For example, for metals. And here, I just want to emphasize that I will only look at the non-dissipative case, so it will be purely negative. And if we add these two into the Maxwell equation, we get this equation. And if we further assume a transverse magnetic polarization, for example, we get just an Helmholtz equation of this form. That I will, so this is for the motivation, that I will simplify a bit for my model to be really simple. So I assume that I have a bound open set of Rn, where n is 1, 2, or 3, to be simple. And I assume that this bound omega set is split into an omega minus part and an omega plus part. And the interface between the two is denoted gamma. And that we have a function sigma, such that sigma is negative in the omega minus part and positive in the omega plus part. And I need to assume that this kappa function is an L infinity function. I will need some T-coercivity assumption that I will detail just a few in few slides. And so the problem I look at is for lambda, a scalar lambda, find a function u in H10 such that it satisfies this Helmholtz, so it's a heterogeneous Helmholtz equation with a nonlinear term. Here we just put a cubic term. And a sigma change of signs. So this is where it's more difficult. And so this equation, we can directly see that this equation has a lot of solution, because for any lambda, u equal 0 is a solution. And so we have actually a set of what's called trivial solutions, which are all the solution of the form lambda 0. And the question is, does there exist non-trivial solution to this equation? And we have two types of result. The one that I call bifurcation result, where here it's more of an, let's say, eigentype result, where the unknown are lambda and u. So we're looking for a non-trivial solution in lambda and u. And some variational result, where here you fix lambda and you're trying to find u, non-zero u that satisfies this equation. And for the second one, we will need additional assumption, but I will obviously detail everything when we get to this result. Okay, so this is for the model. And now I will, so before doing some nonlinear things, we need to talk a little bit before about the linear theory. And here, since we have a sign changing operator, we need to actually do some assumptions. So here, the linear part of the operator is, here I have replaced this kappa u cube by just a source term f, an L2 function. And I directly transform this equation into this variational equation on H10. And I call this term A of AU. This is the principal term of my equation. And this, so this is a quadratic form. And since sigma change of sign, this form is not coercive. It's even not weakly coercive. It's indefinite. And so this is not a semi-bounded operator. And this is what's make this problem complicated. And so we need to add an assumption. And this assumption is this T-coercivity assumption. And so this is, there exists a bound invertible operator T from H10 to H10, such that this quadratic form here, AUTV is coercive. And so that means that there exists actually a constant C such that AUTU is greater than that constant times the H10 norm of U, which is just by definition the L2 norm of the gradient of U. And so this assumption was made to study this kind of sign changing problem. And in the following, I will not do any assumption on the interface or the domain or the function, but actually this assumption, in this assumption is hidden some shape assumption of the interface. More than just regularity. We will see why just in a bit. And for those who know a little bit about this kind of T-coercivity assumption, everything in my talk will also be true if I replace this T-coercivity assumption by this weak T-coercivity assumption. But for simplicity, I will just restrict to T-coercivity assumption. And so now we have this nice assumption, but the big question is, how do I verify this assumption in practice? And when do we have this T-coercivity assumption? For example, in any dimension, if your domain is actually, or at least omega plus or minus is symmetrical with respect to the interface, for example, the square, then we know that the operator is T-coercive only and only if the contrast, which is sigma minus divided by sigma plus, is different than -1. And to show this, that this is true, the T operators that you need to construct are those two, the T plus and T minus. And this T operator use some geometric property of the interface. So here you see that the T actually depends on this R, and R is just a reflection with respect to the interface. So in that case, it's really easy. And this has been done in this paper. Well, okay, we have a nice situation in which we know that we have this T-coercivity property, and we can have other type of shape also. For example, in dimension 2, here it's pretty much well known when do you have T-coercivity or not, and some other example are here. And this is why I say that this T-coercivity hides some shape assumption on the interface, because here, if your interface has a corner, actually the angle of the corner will play a role. And in that case, you have that the operator is T-coercive only if the contrast is outside of a critical interval. And for here, it's -3, -1/3. And yeah, outside of this interval, you are T-coercive, inside you are not. And for example, for this situation, you have that you are T-coercive if you are outside of the same kind of critical interval, and this alpha depends on the angle theta. That is, it has an explicit formula, but it's too big to fit on the slide, so I didn't include it. But you know exactly when do you have T-coercivity. Okay, so now we know when this at least we have example where this T-coercivity is verified. And so there is also example in 3D, but in 3D it's become more complicated when you have corners or wedge and stuff like that. So let's stay simple here. Okay, so now I need to actually know a little bit about my linear part of my equation. And so I will transform my variational equation into an equation of H1, 0. And this is due by the Riss theorem. And we can, so this is actually AUV, where A is a self-adjoint and bound operator from H10 to H10. And I can transform the integral of UV into a CUV, and this is the scalar product on H10. And the C is basically just the inverse of the Dirichlet Laplacian, which is a bound operator from N2 to H10. And so my equation, once you have written these two identities, that equation can be turned into this one directly. And we have that our equation is equivalent to this one. This is an equation only posed on H10. But we want to go a little bit further to show that our equation is well posed. This linear part is well posed. And to do that, we transform this equation into this one, where we basically just multiply by the inverse of A to get this. And this equation is nice because now K is a compact self-adjoint operator on L2. And this gives you that the linear problem is actually a Fredholm, is well posed in a Fredholm sense. And the proof is not so difficult, because this is where you actually use this T-coercivity assumptions, because you can write A as this, and you know that the T star A, where the star is just the adjoint, is invertible, and this comes from the fact that this quadratic form is coercive. So this is where this T-coercivity is used. And now I can define this K, that is just A minus 1C, which is a compact operator from L2 to L2. And it's self-adjoint by using this chain of identities by playing with the definition, basically, of the scalar product on L2 and H10. So now we know that the linear problem is well posed in a Freudian sense. So we will need this in a bit in the nonlinear part. But we need a little bit more. We need to know about the spectral property of our operator. And here we have a nice compact operator, K. And so we look into the spectral property of K. And since K is a compact self-adjoint operator, there exists an L2 orthogonal basis of eigenfunction associated with the eigenvalue sequence mu G for the operator K. And we know that this eigenvalue sequence can only accumulate at 0. And we actually know a little bit more that we have a positive set of eigenvalues that will accumulate at 0 and a negative set of eigenvalues that will accumulate to 0. So we have an infinite amount of positive eigenvalues and an infinite amount of negative eigenvalues. And moreover, we have this weak value on the eigenvalues. So the existence of the eigenvalues is done in this paper, and we had this weak value based on Max characterization of the eigenvalues. So now we know a bit about the spectral property of K, but we would like to go back to the spectral property of the operator. And so now we do the link between basically the eigenpairs of K and the eigenpair of the operator. And so now there is a sequence of eigenpairs of this operator, such that so basically the lambda are the inverse of the mu. So since the mu goes to 0, and there are a positive sequence of mu going to 0 and negative sequence of mu going to 0. Now, when I take the inverse, I get basically a sequence of lambda that will go to minus infinity and to plus infinity. So I have a discrete spectrum that goes from minus infinity to plus infinity. And the eigenvalues, the eigenvectors, so form orthogonal basis in L2. And in H1, I just know in H1 that they are dense in H1. And they satisfy this Kronecker product, basically. So this is just saying that this is orthogonal in L2. And here, since sigma change of signs, just tell you that it has nice product property, but doesn't tell you that if it's a basis or not. And from the weak very low, we have an upper bound on the number of eigenvalues of this form. Okay, so if we summarize a bit, we have, so for the linear part, we know that the problem is well posed in a Freudian sense. We know that we have a discrete spectrum. And just to visualize a little bit what these eigenvalues look like. So for example, for a 1D example, so here omega is just the interval minus 5. The interface is at 0, so I have the symmetrical intervals. And in this case, sigma is constant, here minus 1.1, and sigma plus is constant equal to 1. And here I plot the, let's say, the smaller in magnitude the eigenvalues. And you can see that the positive eigenvalues will be oscillatory in the positive part of the domain and exponentially decreasing in the negative part of the domain. And for the negative eigenvalue, it's the opposite, no matter the value of sigma minus. And we have an additional eigenvalue, this hat eigenvalues, which can change of signs depending on if sigma minus is smaller or greater than -1. Okay, so this is just to visualize the eigenvalues. And now we will go to the first nonlinear result, which is some bifurcation result. So first, to illustrate the bifurcation result, so here we are on the nonlinear part, it's useful to introduce what is called a bifurcation diagram. And so to introduce that, we will look at the bifurcation diagram for a very simple equation, the Dirichlet Laplacian, with actually no nonlinear term. It's simple. And so the bifurcation diagram is basically a visual representation of the set of solution. However, the set of solution lives in R times H10. So it's too big. So for visualization purposes, we will project this set of solution into this bifurcation diagram. So in the x-axis, I put lambda, my scalar parameter lambda. And in the y-axis, I will put the L2 norm, for example, of U. And so in this diagram, so we already talked about the trivial branch. The trivial branches are all the solution of the form lambda 0. So they are all solutions. And for this equation, this is a simple eigenvalue solution. I actually know already what this bifurcation should look like. So I need to introduce the eigenvalues of the Dirichlet Laplacian. And I know I will have a branch emanating of each eigenvalues that I can parameterize like this, like lambda j fixed and s sigma phi j, where phi j is the eigenvector associated to lambda j, and s is just the parametrization of this half-line. So this is the bifurcation diagram for this simple equation. And now, if I add a nonlinear term, a u cubed, I still have my trivial branch. I still need to look at my eigenvalues. And now the branches that will bifurcate from this trivial solution will not be straight line, but will be some curve in this representation that is parameterized by this parameter s. So this is what it's called a bifurcation diagram. So we bifurcate from these eigenvalues and have some curve. And so each point of this curve will correspond to a non-trivial solution. Let me rephrase that a little bit, because here we do a projection. And so actually we can a little bit hide information. So for example, in this equation, if lambda u is a solution, lambda minus u is also a solution. So technically along this curve, you have two solutions. One corresponds to plus u and minus u. And other things is that in this representation, line might cross one line can cross another line, but that does not mean that actually they really cross in the space R times H10. Just mean that they might have the same norm. So you need to be careful when looking at this type of diagram. Okay, and so if I change, so here the only thing I did was to change the sign of the non-linearity and get the branch in the other direction. Okay, so for the first part of the result, so I recall, so our equation is this one. And the first part of the result is saying that for all the eigenvalues that we have found in the previous section are bifurcation point for this equation. So the bifurcation point, so first, what is a bifurcation point? So the definition of a bifurcation point is that there exists a sequence of non-trivial solutions that actually converge to the trivial solution. So if I just go back, so this is a bifurcation point because you have a sequence of non-trivial solutions converging to this bifurcation point, to this point. And so what we're saying is that all the eigenvalues are bifurcation points. Actually, it's easy to see that the bifurcation points can only be the eigenvalues of the operator. And here we are saying basically the inverse. We think that all the eigenvalues are bifurcation points independently of their multiplicity. Just to introduce some a small notation, we call Cj, which will be the branch emanating from the bifurcation points lambda j 0. So if I just go back in time, if this is lambda 1, this will be C1, and this is the connected component which is linked to this bifurcation points. Okay. And we also have some Taylor expansion at these bifurcation points. So this is this can easily be done with perturbative methods, and we see that the Taylor expansion depend on the eigenvectors associated to the eigenvalues, and we see, for example, that the first derivative is always 0, and the second derivative will basically depend on the sign of kappa. If kappa is positive, this will be negative, and if kappa is negative, it will be positive. So if I go back, so this is why it starts with a vertical tangent here, because the first derivative in tau is 0. And as I say, the sign of the second derivative will be basically the opposite of the sign of the non-linearity here. So this is why here I have a minus, they go to the right, and here I have a plus, they go to the left. Okay. So as for the proof of this result, if the eigenvalue have a multiplicity 1, we can actually use a very known theorem of bifurcation theory, which is the Kondal-Rabinovitz theorem. But here we are saying that all the eigenvalues are bifurcation point independently of their multiplicity, and this is the more difficult part because this the proof is based on this energy functional. So from this equation, we can deduce an energy functional psi lambda q, which is this, and this energy functional is strongly indefinite in the sense that the principal part of this this energy functional is sign indefinite. So sigma, since sigma has a change of signs, that means I actually have an infinite subspace for which this part is positive, and also I have an infinite subspace for which this part is negative. So this is why it's strongly indefinite. And this is difficult, but however, the critical point of this energy functional still verify our linear equation on H10 that we have written in the previous section with some nice property, because A is an invertible self-adjoint Fredholm operator and C is a compact positive self-adjoint operator. And so we can still do a bit, and the proof is based on abstract results, some recent abstract results for this strong indefinite energy function. Cool. Yes, so and to just put some picture on the results. So for example, this is the bifurcation diagram. So this is a 1D example for this equation. And here I have, so I'm on the interval minus 5. The interface is at 0. I have put this parameter for sigma plus. And this is done using the code PD2Path, which is a MATLAB package to compute this bifurcation diagram. And so here we see that we have, so we should have other eigenvalues, but we need to start with a finite number of eigenvalues. And so we see that we have this nice branch, and we can see that this goes to the left because here we have a positive kappa function. Okay, and we also did the bifurcation diagram for a 2D in a 2D setting. So here we have basically two squares that we have glued together, and we see the same kind of curve, and this is why I have insisted earlier about the point crossing. Here we didn't verify, but we are pretty sure that this point is not a double point. I mean, the curves don't cross in the full solution space, but you just have two solutions with the same norm here. Okay, but we actually can say a little bit more about this branch, which is this. So this CJ branch, this connected branch coming from the bifurcation points. We know that if the eigenvalues has odd multiplicity, then the branch will satisfy what's called the Rabinowitz alternative, which means it can only do two things. Either the branch is unbounded, in a sense that it leaves any bound set in the R times H10 solution space, or if it's bounded, it must contain another trivial solution. So if I go back here, that means either the branch will continue, I don't know, but somewhere, and will leave any bound set, or it will actually go back to the trivial solution, to the trivial branch solution. Okay, the proof comes from this Rabinowitz theorem, and one way to rule out the two alternatives is that if I can find a property that is constant along the branch, but different from different branch, then I know that okay, if a branch actually connects two bifurcation points, I mean, this property must be the same, and if it's different for the two bifurcation branches, two cannot happen. And we can actually verify this in our 1D example, because in that case the eigenvalues are simple, so in particular they are odd multiplicity. And by counting the number of zeros of our eigenvectors, we can roll out the second alternative. So here, so here what is important is that the connecting branch connecting one bifurcation points are unbounded and cannot cross another branch, because actually the number of zeros is preserved. I mean, even more precise than that, but the number of zeros in each subdomains, so omega plus and omega minus, are preserved along the branch. So, for example, for the eigenvalues that are negative, we have j interior zeros in omega minus, and we know that and we have no zeros in omega plus, and this will be true along the branch. And for these hat eigenvalues, we know that we have no interior zeros, and along the branch we still have no interior zeros. And for the positive ones, we have j interior zeros in omega plus and no zeros in omega minus. So again, to visualize a little bit more precisely what I'm just saying, for example, if we look at this branch C minus 2, so this is a sequence of, this is along the branch C minus 2, so this is very close to the start. This looks like the eigenvalues, the eigenfunction, and we see that we have two zeros in the negative part and no zeros in the positive part. And as we go along the branch, so the solution is a little bit different, but we still have two zeros in the negative part and no zeros in the positive part. Okay, and if we look like at this hat function, and this is the same, you have no zeros anywhere, and you still get no interior zeros along the branch. And if we look at positive eigenvalues, the same, this is 5, so we choose at 1, 2, 3, 4, 5 zeros, and this stays the same along the branch. Okay, I think I will go maybe a little bit quick on this variational part. So for the variational results, I need an additional assumption, and this additional assumption is that I need some kind of half with basis property on these eigenvalues. So precisely what I mean is I need this estimation on the eigenvectors and eigenpairs of our operator. And this is half of a with basis property, because a true with basis property will mean that you have the upper bound and the lower bound. And here we only ask for the upper bound. Okay, and so this assumption in red can be verified in this 1D example, because we have access to explicit expression, but in a higher dimension, we actually don't know if it's true. Okay, so how much time do I have left?
You can have 10 more minutes if you need, Zoïs, as long as you need.
Okay, I think I would not into too much detail here.
Please go ahead.
So here for the variational result, now you fix lambda and you ask how many solutions do I have when I have fixed lambda and I want to find u. And this is also based on this energy functional, and this is based on you need to rewrite your energy functional to look like this. And this is correspond to the nonlinear part, and this corresponds to the linear part. I don't tell you what is exactly this norm, and either this U plus or U minus. But I mean, I tell you now, so we have fixed lambda, and we introduce a new scalar product and the new norm associated to it, which is just this one. So you take, so phi I and phi j are the eigenvalues, and you write this like this. And so this is a new scalar product, and you define the space H, which is the completion of the mode with this scalar product that depends on that. And then this, so this explains this norm, and this U plus and U minus are just the projection basically on the subspace where lambda j is less than lambda. This is equal. E0 can be just 0 if no lambda j equal to lambda, but here you can have something or nothing. And E plus is the one where lambda j is greater than lambda. And and then you take the projection from H to this plus or minus. So basically you just project into this to space. You define A plus as the projection of U in this to space. And then it's a straightforward computation to actually show that this line is actually equal to this line. And so the big, where do we need this additional assumption is that it's here, because we need that the space H is a dense subspace of H10. And so we have this estimation, and actually this estimation is basically exactly this additional assumption that we need to add. So this additional assumption is here to show that H is a dense subspace of H10. And this is where we use this additional assumption. And if we had this risk basis property, then we will know that H is actually H10, but we don't know that. The only thing we know is that in 1D, this is actually true. And the result is the following. So here we need to also add an assumption on K, that K is greater than alpha strictly positive. And now we know that if you fix lambda, then this equation has actually an infinitely many solution in H. And there exists a least energy solution, which is characterized by this property. And the proof of this result is also based on abstract result for strongly indefinite energy functionals. Yeah, and I think just to illustrate quickly, so here what we say is that this is the same picture as above, but we will see it in a little bit in a different way. Here we say if I fix lambda, so here I take a straight line with a fixed lambda, then that means there is an infinite number of solutions. So that means my straight line will should actually, I mean, an infinite number of branches should cut this straight line here. So this is what the variational results are. And I think, yeah, almost finished, yes. So what we did, we have a proof, so bifurcation and variational result for this Helmholtz equation with sign changing, diffusion coefficient, and nonlinear term. And we have some open question. Can we find sharp very low for the eigenvalues? What happened when you have a double sign changing? So that means now I had here a coefficient which is also sign changing. Can we rule out this Rabinowitz alternative 2 in higher dimension? We prove in 1D, but in higher dimension, it's more difficult because the nodal pattern are more difficult to track, and also we don't know if the eigenvalues of our operator is actually a Riesz basis or not. We prove in 1D we prove half Riesz basis property, but not the other half. And yes, thank you for your attention.
Thank you very much, Zoïs, for this wonderful talk. So I would like to encourage people in the audience to come forward with their questions. They could be technical or just, layman questions. So anyone wishing to ask a